All right. So, like I said, the first 2/3 or so of the lecture today, I'm going to spend developing some of the topics we talked about last time. And then for the remainder of the lecture, I'm going to go over the exam and what to do. So last time we began our second module of the class. So we transitioned from flow and single pipe systems or pipeline systems to pipe networks. So this is networks consisting of interconnected pipes. We looked at an example of a branched pipe network consisting of 3 tanks that drain to a common point with some demand leaving the system. And we showed how we could solve this pipe network problem in Excel. So we showed how we could model this system from first principles and actually solve for all of the internal flows and pressures within the system, just using the conservation of mass and conservation of energy. So today we're going to look at a slightly more complex case. I'm going to start this problem and then I'm going to hand it off to you. So this activity is going to be due next week because I don't want to overload you with too much stuff this week. But you should have enough time in class this week to complete it. So in particular, we're going to be looking at a looped pipe network. So previously, we just looked at a branched pipe network. Today, we're going to look at a more complicated looped pipe network that's going to look something like this. And we are going to solve, again, for all of the pressures and flows within the system. Yes.
Do you have a in-class assignment Wednesday?
No, it was just a walkthrough. So I did the whole example up here. So for this case, I will start the problem and then allow you to complete it as an in-class problem. So with that said, go ahead and go to Canvas and under quizzes, there's a problem listed as in-class looped pipe system. And this is the description of the problem. So we have a looped pipe system consisting of 6 different conduits and 4 different junctions with 1 reservoir. There is a single demand flow rate leaving the system of 0.25 cubic meters per second. For each of the nodes, we have the elevation, so the elevation of the ground surface. So nodes 1, 2, 3, and 4 have a ground elevation of 0 meters. The elevation of the water surface in the reservoir H5 is 100 meters. And then for each of the pipes, we have this table of data listing the length of the pipe in meters, as well as the diameter of the pipe also in meters. Okay, so we have all the information needed to set up the problem. Note that we're also going to be using the Hazen-Williams equation for all the frictional losses with a Hazen-Williams coefficient of 100 for all pipes. And we're going to assume no minor losses. So this is the general problem setup. Let me go ahead and just draw out this problem. So we have some reservoir and it's feeding this pipe network. We have a water surface elevation in the reservoir of H5 is equal to 100 meters. This reservoir feeds into a junction, which I'll call junction 1. And then we have this junction splits off into 2 other junctions, junctions 2 and 3. Junctions 2 and 3 are also connected by a pipe. And then junctions 2 and 3 both connect to another junction, junction 4. There is a demand of 0.25 cubic meters per second. So I'll call this Q out. There's a demand of 0.25 cubic meters per second leaving the system. We're going to assume Hazen-Williams coefficient equal to 100 for all lengths. Or so I'll say for all pipes. And let's number these pipes as well. So the pipe connecting the reservoir with junction 1 will be called pipe 1. This pipe here will be called pipe 2. This pipe here is pipe 3. This pipe here is pipe 4. This pipe here is pipe 5. This pipe here is pipe 6. So in pipe 1, we have some flow rate Q1. In pipe 2, we have some flow rate Q2, etc. So I'll just write Q1 just to remind you that pipe 1 has a flow rate associated with it at Q1. The same indexing scheme applies for all of the other pipes as well. And we have our table of values for the lengths and diameters. So the lengths delta X for pipes 1, 2, 3, 4, 5, and 6 are 250 meters, 400 meters, 300 meters, 600 meters, 350 meters, and 450 meters. For the diameters, again, we have 0.3 meters, 0.2 meters, 0.3 meters, 0.15 meters, 0.3 meters, and 0.2 meters. So our goal is we're trying to solve for all of the internal states of the system. So we're solving for Q in all pipes. And we're solving for the pressure head, or the pressure, I'm going to write it as pressure head, P over gamma, in all junctions. Okay, so what is our general approach for solving pipe network problems? What do you remember from the last class session? There's two basic rules we're going to apply. Yes. Exactly right. So we're going to apply the energy equation across each link, and we're going to apply continuity around each junction. So let's start with continuity. The first thing we have to do, even before we do that, is, does anyone remember what we need to do first before we can apply these equations? We need to decide something. Yeah, we need to decide a nominal direction of flow for each link. So I'm just going to assign it this way. Let's say that the flow is going this way in link 1, this way in link 2, this way in link 3, this way in link 4, this way in link 5, and this way in link 6. So for these looped problems, it's often very difficult to know a priori which direction the flows are going to go in each link. So we just have to make a guess. If our flow rate turns out negative, that means that we guessed wrong, but it'll still be okay. Okay, so these are the nominal directions I've decided for each link. Let's go ahead and apply continuity around junction 1. So for junction 1, how can we write the continuity equation based on this drawing here. Yes. Very good. So we see that Q1 is going into the node, Q2 and Q3 are going out. So we have that Q1 is equal to Q2 plus Q3. And as is the general convention in this class, we can rearrange it. 0 is equal to Q1 minus Q2 minus Q3. This will help when we go to formulate our Excel workbook later. Okay, let's just do it for one more so you can get the gist of it. All right, let's pick junction 4. What is the continuity equation for junction 4? Yes. Q4, exactly. So it's Q out is equal to Q5 plus Q6. So junction 4, we have that Q5 plus Q6 is equal to Q out. Yep. And then we can rearrange it just like before. So we have that 0 is equal to Q5 plus Q6 minus Q out. So basically this procedure needs to be applied to each junction, and you'll end up with 4 different equations for continuity at the nodes. Okay, let's try applying the energy equation. And energy gets applied across each link. Again, we're going to follow the same nominal flow directions that we established before. So when I apply energy across link 1, I'm going from the reservoir to junction 1. You know, when I apply energy for link 2, it's going to go from 1 to 2. So we have to follow the same directions here that we use for continuity, or else we'll end up with the wrong answer. So let's go ahead and just start by applying the energy equation across link 1. So for type 1, we can write our energy equation. So this is the same energy equation we've been using since the beginning of class. We have, I'll call it P5 over gamma, because I'm calling this reservoir 5. P5 over gamma plus Z5 plus U5 squared over 2G is equal to P1 over gamma plus Z1 plus U1 squared over 2G. Okay, so node 5 is a reservoir. So we know that 2 of these elements go away. So the pressure at the surface of the reservoir is 0. The velocity at the surface of the reservoir is 0. And our elevation, this is equal to our given value, H5 is equal to 100 meters. Let me give myself a little more space here. All right. So we have the pressure head at node 1, the elevation head at node 1, and we have the velocity head at node 1. What is the elevation head at node 1? 0 from the table of values I gave you before. So if we go back to our table of values, oh, sorry, it's not shown on this slide, but in the problem statement on Canvas, you're given that the elevation for each of these nodes is 0. In other words, the reservoir is 100 meters, the water surface in the reservoir is 100 meters above the actual junctions and the water distribution network. Now we're left with this interesting term here, U1 squared over 2G, where U1 is actually referring to the velocity at the junction. So the velocity at the junctions for pipe network problems is not really well defined. Keep in mind that velocity is a vector quantity. And so at the junctions, the direction at which the velocity is applied isn't necessarily well defined. So what we're going to do is we're just going to assume that the velocity at junctions is zero. So this is a pretty safe assumption, especially when you have some kind of mixing occurring at the junctions or flow going off in different directions. So we're going to assume that the velocity at the junction is equal to zero. Oh, I forgot one term here. What did I forget? The head losses, very good. I stayed up very late finishing this test, so. So to the right-hand side of the equation, we have to add the head loss from 5 to 1. So we can rewrite this. This is now going to be H5 is equal to P1 over gamma plus the head loss from 5 to 1. So I said that we're going to use the Hayes-Williams equation for the head loss. So just like last time, I'm going to try to do this from memory, and if I'm wrong, let me know. This should be the sine of Q1 times 10.7 times delta X divided by D1 to the 4.87 power divided by the Hayes-Williams coefficient to the 1.85 power. That's a 1.85 times the discharge in pipe 1 to the 1.85 power. And someone just very quickly check if that is the correct expression for Hayes-Williams. Okay. So that's the general procedure. We can do the same thing for, let's say, pipe 2. So let's just very quickly do that. For pipe 2, we have P1 over, sorry. What are we going from here? Yeah, P1 over, so we're going from 1 to 2. So this would be P1 over gamma plus Z1 plus U1 squared over 2G is equal to P2 over gamma plus Z2 plus U2 squared over 2G plus the head loss from 1 to 2. So just like before, elevation at both junctions is 0. The velocity head at both junctions is 0. So what you end up with is P1 over gamma is equal to P2 over gamma plus the head loss from 1 to 2. And we can use our Hayes-Williams equation to express that head loss in terms of our discharge. So this is going to be sine of which Q? Q2. So for pipe 2, this contains the discharge Q2. The flow rate in pipe 2 is Q2. So there's going to be sine of Q2 times 10.7 times the length of pipe 2 divided by the diameter of pipe 2 to the 4.87 power divided by the Hayes-Williams coefficient to the 1.85 power times the absolute value of Q2 to the 1.85 power. And you can see the pattern we applied. Yes. So okay, so this quantity here refers to the velocity at the upstream junction. This quantity here refers to the velocity at the downstream junction. This quantity here refers to the head loss across the pipe. So for here, we use the average velocity in the pipe, or which would be, yeah, the mean velocity in the pipe. So they're using different velocities. This notation is a little bit confusing because U1 here actually means velocity at node 1. But good question. So the basic procedure is we write out our energy equations for each link, we write out our continuity equations for each node, and then we create a system of equations that we solve simultaneously using a numerical solver like the solver in Excel. So what I've done is I've uploaded a starter spreadsheet for you. If you go to Files, Lecture 10, there is an Excel workbook called Looped Example Starter. Go ahead and download this. And I'm going to open it up. It looks big, but just start by filling in the different cells. So the first 6 rows here are just the length of each pipe. The next 6 rows are the diameters of each pipe. The next 5 rows are the elevations of each junction, where 5 refers to the reservoir. The next 4 are the demands at each node. So all of these are 0 except for junction 4. And then the rest are just your known parameters: Hazen-Williams coefficient, pi, acceleration due to gravity, and density of water. So after that, you can compute the cross-sectional areas of each pipe, and then you can compute the head losses using the Hazen-Williams equation. Once you do that, just like before, we're going to set up our energy equations for all 6 links. I've specified the nominal directions to use right here. And then the continuity equation for each junction. Remember, these are all expressed with 0 on one side. And then your decision variables are these 10 variables here. So the flow rates in each link and the pressure heads in each junction. So what I'm going to do is I'm going to give you the next 15 or 20 minutes to work on this with your neighbors. I will check back in with you in about 15 or 20 minutes, and then I'm going to talk about the exam. Okay, so take the next 15 or 20 minutes to work on this problem, and raise your hand if you have any questions. So we'll continue this example on Thursday.